computer-oriented cosmology. So today's going to tell us about two of his papers. We're going to have a speaker dinner for Emmanuel at 6:30. Everyone's encouraged to come. And Emmanuel's here until tomorrow afternoon, right?
That's right.
If you'd like to meet.
Cool. Thanks a lot, Kendrick, for the introduction. Thank you for the hospitality and the possibility to present my work to you today. So I would like to present to you two ways of using the cosmic microwave background as a backlight for the large-scale structure. So these are two methods that I think are very promising to constrain uncertain physics and systematics in the large-scale structure from the CMB. So this talk will basically be split into two parts. And I'll first talk about lensing systematics, shear calibration, and how CMB lensing can help with this. And second, I'll talk about the kinematic Sunyaev-Zeldovich effect. I'll present to you a measurement of this effect and what we hope to learn from it about the gas inside galaxy clusters. It's the simplest statistics you could have dreamed of. If you look at a map of the cosmic microwave background, you basically have a Gaussian signal and a Gaussian noise. And so to simplify grossly, basically you just Fourier transform this, measure a power spectrum, and that's basically the end of the story. And finally, on top of all this, these primary anisotropies in the cosmic microwave background have been measured extremely well, almost down to the cosmic variance, which is the ultimate limit. Right, so I think these three bullet points summarize why the cosmic microwave background has been such a good probe of cosmology. So there still certainly remains very important fundamental physics questions to be answered from the cosmic microwave background. Things like the number of relativistic species, detection of primordial gravitational waves. But I think this last bullet point is also a motivation to ask what is there to learn beyond these primary anisotropies of the cosmic microwave background. How do we go further? And one very tantalizing way of doing this, of going beyond the primary anisotropies of the cosmic microwave background, is to look at the large-scale structure. And to me, the large-scale structure is this very tantalizing thing. And I say tantalizing because on the one hand, you have the promise of this gigantic statistical power. And that's due to the fact that you're probing a whole volume of the universe as opposed to just the surface. And so the number of modes, of Fourier modes that you can access is basically huge. Scales as the cubed as opposed to the square of your resolution of your experiment. But on the other hand, accessing this information, the information that's in this gigantic statistical power, is complicated because of several reasons that I tried to list here. On the one hand, you're dealing with nonlinear physics, the evolution of perturbations, these acoustic waves that now collapsed and became large. And as we all know, nonlinear physics is always trickier than linear physics. A consequence of this nonlinear evolution is a more complex statistics. So the Fourier modes that were initially independent and Gaussian are now no longer independent and no longer Gaussian. So the power spectrum is no longer the end of the story like it was in the previous slide. This is something that I tried to illustrate on this plot. Here, I showed some signal-to-noise ratio or some measure of the information content of your experiment. That's in the case of with gravitational lensing, but that's a detail. As a function of the maximum multiple or smaller scale that you can access. And what you see is basically what you would get if the field were Gaussian. And because it's non-Gaussian, the information in the power spectrum is actually smaller than what you would get in the Gaussian case. And one way to think of this is that the information has now moved away from the power spectrum into, for example, bispectrum and higher point correlation function. So what's the best way to recover all this information? Do you go to bispectrum, trispectrum, and keep going? It's basically not an answered question. On top of this, in the large-scale structure, the baryons get involved in complex effects that basically complicate the relation between what you actually observe, the stars and the galaxies, and what you'd like to know, which is the matter density field. This is the issue of biasing. And on top of this, the baryons behave differently from dark matter on small scales, and this complicates the matter power spectrum. So this is what I showed, the matter power spectrum with baryons with respect to without. And what you see is that baryon cooling increases the density on small scales, forms stars, and a variety of feedback effects push the gas away from your halos. And so you get basically a complicated, uncertain shape of your matter power spectrum. So that's it for my summary of the large-scale structure. During my PhD, I got a chance to touch on each of these topics a little bit. So these are projects that I won't have time to talk about today, but I'm pretty excited about. And so if you're interested in any of these, please come find me. I'll be around all day today and most of the day tomorrow in the visitor office. So one of them was about how to jointly analyze correlated non-Gaussian observables of the large-scale structure, and basically taking into account the effect of couplings between large scales and small-scale modes. The second one was about trying to predict the nonlinear matter power spectrum, this nonlinear evolution, and this was a test of this effective field theory for the large-scale structure. This was a test of the theory compared to simulation, and the specificity of this project was that this was a test not just at the power spectrum level, but actually at the field level and free of cosmic variance. And finally, recently, in collaboration with a French graduate student, Cyril Doux, we made the detection of a bispectrum between the Lyman alpha forest and the CMB lensing. And the origin of the signal is basically the same as here. It's a nonlinear effect due to the coupling between long and short modes. So if you're interested in any of these, please talk to me. But that's it for what this talk is not about. Moving on to what this talk is about, I will first tell you about shear calibration with CMB lensing, and then talk about using the kinematic Suniev-Zeldovich to learn about the physics inside galaxy clusters. And so these are, I think, two promising approaches to use the cosmic microwave background in order to learn about the large-scale structure. Shear calibration with CMB lensing. This is a project work done in collaboration with Elisabeth Krause, Tim Eifler, Olivier Doré, Hironaomi Miyatake, Jason Rhodes, and my advisor, David Spergel. And to give you a little bit of introduction, I think everyone knows about gravitational lensing, which is how mass deflect light or how galaxies smile at us from the other side of the universe. But in the weak regime that I'll be interested in, the effect is much less spectacular, and you're typically talking about a 1% shear, a 1% distortion of the shape of the galaxy, which sits on top of an intrinsic 20% shape. So we're talking about a very small effect. Why this is interesting, and in particular, what information is there that you can't just have in galaxy clustering, for example. One point is the fact that you probe both geometry and growth. And if you think of it in terms of general relativity and the Bardian potential, you basically probe the sum of the two as opposed to just one. Intuitively, this is this factor of 2, that you get in GR for gravitational lensing. Another good point is that you probe all the mass as opposed to just looking at the galaxies that you see. And because of this, you are more free of this biasing issue of how do galaxies trace the dark matter. And here's just a very quick picture to try to give you an idea of how hard it is to measure these distortions. What you basically do is, you start with your galaxy. That's how it would look like in the absence of lensing. This is a big exaggeration of what it looks like in the presence of lensing. And then you look at this galaxy through your telescopes, pixels with noise, and you're basically trying to measure the ellipticity of this object. So I think this cartoon sort of shows that it's going to be hard. In fact, it underestimates a lot how hard it is to do it. And this is the issue of shear calibration. So the way this works, typically, is that you try to relate the mean ellipticity of your galaxies to the true shear, the true lensing deflection. And this is one way of parameterizing it. Basically, you have a lot of effects, additive biases, leakage from the ellipticity of the point spread function, which is the resolution of your telescope. And you also generically get multiplicative factors, multiplicative errors in your calibration. So this is what we call the shear multiplicative bias or shear bias, and this is what I'll be focusing on today. So why this systematic effect is important is because this little m that you see here is degenerate with the amplitude of your signal. It may vary with redshift, and therefore it's degenerate with the growth history. And because of this, it may mimic the effect of a dark energy equation of state. So basically, you're doing this gravitational lensing in order to learn about dark energy. One of the ways that you try to learn about it is to look at how the growth of structure evolves with redshift. And that tells you about the equation of state of dark energy. So you'd like to get that right. Because this systematic effect is so important, the requirements for future upcoming experiments, like the Large Synoptic Survey Telescope, are very stringent. So basically, you need to get this number small to below 0.5%. And this number of 0.5%, this requirement, should be compared with what's currently achieved, what's the state of the art. And the state of the art relies on image simulations, which means that you build a whole simulation where you think you have realistic images of basically the galaxy populations in your sample. So you assume that you understand the galaxy population, and you assume that you understand the individual morphologies of all your galaxies. And what you get currently, this is the state of the art, you get to level of a few percent. What that means is that if you want to reach the requirements for something like LSST, you need a factor of at least a few better than this.
Are these figures of 3%, 5%, and 1%, are those the estimated systematic error on a Monte Carlo-based calibration? Mm-hmm. Or are you saying that's the difference between what you get when you Monte Carlo calibrate and what you would have guessed?
So it's hard to actually estimate the size of these errors because they're dominated by your uncertainties on your modeling of the galaxy population and morphologies. And so that's why even the current numbers that are quoted here and that are already far from requirements are themselves pretty uncertain. And oftentimes the way people estimate these numbers is that they have two independent methods for measuring the shear, and they compare the two. They find an error over the size, and they say, I have an estimate of the variance based on 2 data points. So I think that gives you an idea of how scary and difficult this is. And fundamentally, the reasons why this is difficult are listed here, but instead of going into detail, I would just show you what the state of the art is. So this is shear calibration for the dark energy survey. So again, this figure of 3 to 5%. And what you see here is a null test. So they have 2 different independent ways to estimate the shear. They take the difference between the 2, and the correlation function of this is a function of scale. So you see data points that you would expect to be consistent with 0. And what happens is that while each method independently passes all of the null tests and would be accepted as a valid method, the 2 differ significantly. So this means that even at this level of a few percent, there are residual systematics that we do not understand. So what people do is they say, OK, we're going to throw out these small scales and hope that we're fine here. But that's sort of an optimistic guess, given that you don't understand the origin of this effect. So this basically says that if you care about dark energy equation of state and you try to get it from lensing, you have to be really sure that you can get this shear calibration right. And currently, this is very difficult. So to me, this says that it would be very valuable to have an independent way of calibrating the shear, an independent way from these image simulations. And the idea is just that if you go through all of LSST and you do all the data analysis and you find that the dark energy equation of state is not -1, you'd like to be able to say, well, I'm pretty sure I didn't mess up the shear calibration. And this is where CMB lensing comes in. So I talked about the lensing of galaxies. This is the lensing of the cosmic microwave background. And this is an exaggerated version of what you would see if you had a very massive cluster here at the center. Basically, the way weak lensing manifests itself in the cosmic microwave background is with these arc-minute deflections coherent on degree scales. And what this does, I showed you a power spectrum of the cosmic microwave background. What this does is because it shifts peaks randomly, it smooths the acoustic peaks of the cosmic microwave background. What it also does, and this is the same plot as here, but in log space, is that it adds extra power on small scales. And finally, what it does, importantly, is that it breaks the statistical isotropy. When you look at this picture, even if you don't know what the CMB actually looks like behind, you can see that there's something weird in the middle. And this is the basis for the CMB lensing reconstruction. So this is what CMB lensing is. How does it help with shear calibration? Schematically, it helps in the following way. If your shear or convergence, basically your probe of galaxy lensing, is proportional to a cosmological amplitude times this shear miscalibration, and if your CMB lensing does not have this shear miscalibration, you would think naively that by combining the two, you'd be able to solve for both shear calibration and cosmology. In fact, you can do a bit better than this if your CMB lensing and galaxy lensing measurement overlap. And the reason for this is the following. If you look at the function of redshift, this blue curve is the CMB lensing kernel. It means these are the redshifts that CMB lensing probes. This red curve here is the galaxy lensing kernel, the redshifts that galaxy lensing probes. And what you can see is that there's overlap in this redshift range. What that means is that you can cross-correlate the two. And this basically gives you a third redshift bin somewhere in the middle. So this is very schematically how this would work. Now, what's the value in this method? Well, this would be purely empirical. It would be a self-calibration in that you fit for systematics and cosmological parameters simultaneously, and you let the data tell you what they are. In particular, there's no assumption that you actually understand the galaxy population in your sample or the individual morphologies. So that's the idea, being free of these assumptions. And in fact, this is a method that has known a lot of interest recently, and people are very interested in it. People have started applying it to real data, and currently what you reach is something like 10 to 20% calibration. So far from state-of-the-art image simulations, and even farther from the LSST requirements. And this happens while fixing cosmology and other nuisance parameters. What this means is that people basically assume that we know cosmological parameters and that we're doing lensing in order to measure this little m, and how well do we measure m? But of course, at the end of the day, you're not doing lensing to measure little m, you're doing lensing to measure the cosmological parameters. Yes?
Could you just remind me what is K in this context? So you try and measure sigma A from your galaxies at a particular redshift, and you try and measure sigma A from the CMB.
Right.
It should be different by the spectrum.
Right, sorry. So this kappa here is for convergence. But basically, whether you think of it as the convergence of the shear, really in weak lensing, there's only one scalar quantity. So I'm using them a bit loosely. Right, so this method currently is not extremely competitive. And so the question we wanted to ask is, will it ever be useful in the future? Meaning, can it actually reach a level of calibration that's competitive with image simulations or requirements? And can you do this while varying cosmological parameters? Because again, you don't do lensing to measure nuisance parameters. So this is the question we wanted to ask. And to do this, we performed a forecast for a coming experiment, the Large Synoptic Survey Telescope that I talked about, and a CMB stage 4 experiment. So let me now give you some quick details about this experiment, just so you have an idea of what we're doing. This is the Large Synoptic Survey Telescope. And what I'm showing here is just as a function of redshift, the distribution of your galaxies. The bumps that you see in green and blue are the source bins. That means the bins from which we measure the shear by estimating the shapes of these galaxies. And the bins that I show in reddish here are the source bins, the one that I use to measure the positions of galaxies in order to correlate them with themselves and get galaxy clustering, or correlate them with shear estimates. This is galaxy-galaxy lensing. And finally, you can correlate shear with shear at different redshifts, and that's just what people call cosmic shear. So that gives you an idea of the kind of observables that I'm included in the forecast. That was on the galaxy lensing side. On the CMB lensing side, I assumed specifications for this CMB stage 4 experiment, which people are planning now and is going to happen in the next few years. And this is basically a high resolution, high sensitivity, large sky coverage CMB experiment. And the only thing I'm including from this is the lensing map, the reconstructed lensing map. What you can see here is a plot of the power spectrum of this lensing deflection. And again, deflection, shear, convergence are interchangeable here. The black curve is the signal in CMB lensing, And the colored curves are basically the noise that you get in the lensing reconstruction with different estimators. So the way this works is you use quadratic estimators of temperature, E and B polarization, and each gives you an estimate of the CMB lensing. You can combine them all into a minimum variance estimate, and this gives you an idea of the relative size of the signal and the noise. So basically, an experiment like CMBS4 will measure CMB lensing to very high precision. So this is all I'm including on the CMB stage 4 side. I'm not including any power spectrum of temperature and polarization for cosmological parameters. And again, the observables included in this forecast are galaxy positions, galaxy shear or convergence, these two from LSST, and CMB lensing from CMB stage 4. The forecast includes all the 2-point functions of these 3 quantities, which I'm listing here. Position and position is clustering. Position and shear is galaxy-galaxy lensing. Shear and shear is this cosmic shear tomography. Positions and CMB lensing. Shear and CMB lensing, and the auto power spectrum of the CMB lensing. And the parameters we try to constrain from this simulated analysis are cosmological parameters, galaxy biases for the tracer sample, but most importantly, this shear calibration parameters for each of the different source bins. We also marginalize over photometric redshift errors, which are a big issue for upcoming lensing surveys. And finally, we try to make this forecast as realistic and conservative as possible. In particular, we include all the covariances between all these 2-point functions because they are measured on the same part of the sky and therefore are correlated. And so you don't want to double count the information. So let me now move on to show you the results we find. So these are our results. And what I'm showing here again are these 10 little shear calibration parameters for each of the shear bin. You can read on top the median redshift that corresponds to each of these tomographic bins. And the y-axis is the constraint on this shear bias. So basically, when you run the simulation and you let the data tell you what these shear calibration parameters are, this is the residual uncertainty, the posterior uncertainty. And to set a scale here, this dashed line corresponds to the LSST requirement, again at 0.5%. So ideally, you'd like your method to go as low as possible and to reach this level of calibration.
Can I just ask real quick about the 0.5%? So that is what is required to do what?
Right, right. So there's this, there are these concepts of requirements in LSST, and where they come from is that given your measurement, you have a certain level of statistical error, and the statistical error is going to be extremely small with these huge data sets. And then the question is, how well do you need to know your systematics so that you don't waste the statistical power? So the requirement is set basically by not increasing your error bars by more than 10% of the statistical error. In a sense, this is an independent question from is it realistic and will it ever happen? This is what you would need to not waste your statistical power.
I think he's asking what is the statistic that's being measured. No, actually, that was what I was okay. That addressed my question. All right. I just wanted to know if it was based on meeting some figure of merit requirement for measuring dark energy.
Basically, yeah.
Something like that.
Basically, yeah. And so we explored different combinations for different reasons that I could go in detail if you're interested. But basically, the main curve you should be looking at is that big red curve. And this is the level of self-calibration of this shear that you get when you include CMB lensing and all the observables I showed. What you can see basically is that this curve for the bins that have high redshift, this red curve goes below the requirement. So this means you reach the requirement, that's great. At low redshift, you don't quite do this, and what you see is that this method works better at high redshift. The reason for that is quite intuitive because of the lensing kernel of the CMB that's broad but peaks at high redshift. And so for the galaxies that are at higher redshift, basically the correlation coefficient is going to be higher, and the method will work best. Yes?
So then going back to the question about maybe the dark energy figure of merit,
Mm-hmm.
I mean, then do you lose here now because you've lost all your low redshift?
Right. So
So is this good enough then to actually
Yeah, yeah. So no, that's a good question. So the way you typically think you constrain this equation of state of dark energy is by comparing low redshift to high redshift. And so ideally, you'd like to know the calibration well here and there too. In practice, what you can still do, though, is that even though the calibration is not ideal around here, you still have the galaxy clustering that does not have this issue, but doesn't go to high redshift. So in a sense, you're comparing lensing at high redshift to clustering at low redshift. So it turns out this level of shear calibration doesn't actually degrade things much, whereas no shear calibration or current state-of-the-art shear calibration would. So you're still solving most of the problem. And so again, this is assuming no prior on this calibration, so no image simulations. And this varies cosmological parameters and other nuisance parameters like photometric redshift errors. So this basically answers the question of how well can you do when you have this kind of data set? Will this method actually be useful? And I think the answer is yes. And the fact that the shear calibration works best at higher redshift is also a good point, because this is where your galaxy population and morphologies are even more uncertain. We basically don't know so well what galaxies at redshift 2 look like. And this is where this method is most useful. So let me just conclude this part of the talk and say that this is one way that CMB, the cosmic microwave background, can help with the large-scale structure, constraining systematics in the large-scale structure. And this forecast for CMBS for lensing and LSST shows that you can actually calibrate the shear to 0.5%, which is basically the LSST requirement on most of the redshift range. The value of this method, again, is that it's purely empirical. It's a self-calibration from the data alone, and it doesn't rely on any assumption about the galaxy population morphology. It works better at higher redshifts, where this would otherwise be more difficult. And we checked, but I didn't show in this presentation, that this method is robust to a whole set of other systematics effects that occur in galaxy lensing. So that's the end for this first part of the talk. I should probably pause here in case there are more questions before moving on.
When you say possible with advanced stacks, so on and so forth, possible to get to the 0.5% program?
Right. Yeah, so this is something we checked because people are trying to agree on the exact design of CMB stage 4 right now. And so the question of what sensitivity, what resolution should you have is something that people are interested in. So we basically looked at how well this method works if you vary the sensitivity of your CMB experiment, the resolution, and the smaller scale you include, which is a statement about foreground cleaning, basically. And what we found is that this first row shows, again, the noise in the CMB lensing reconstruction that I showed earlier. And the different curves shows how this varies when you vary noise, resolution, and small scales. And basically, noise matters and varies the level of shear calibration. So this black line is what I had shown. This is the range of how much this degrades when your noise goes down. So basically, it's not catastrophic. And things like resolution and maximum multiple have a very, very small effect on this shear calibration, so they don't matter as much.
What are the noise specs on the side? Does that fall in that range?
Right. I think somewhere between 5 and 10 microcarats minute is what we expect for noise. So that would be this sort of blue-red curve. So not dramatic degradation. All right. So moving on, I'm going to present to you a measurement of this kinematic Sunyaev-Zeldovich effect and what we hope to learn from it about gas physics inside galaxy clusters. So this measurement was made using a CMB temperature map from ACTPol and a galaxy sample from BOSS. So this is my one-slide summary of trying to put them all on the same page. And this was done in collaboration with Simone Ferraro, Mariana Vargas Magana, Kendrick Smith here, Shirley Ho, my advisor, David Spergel, Nick Battaglia and the ACTPol and SDSS collaboration. So first of all, I thought I should motivate a little bit. Why would you care at all about gas inside galaxy clusters if you're a cosmologist? And these are, I think, two reasons why you should care. One of them is that the gas inside galaxy cluster is actually very sensitive to your assumption about galaxy formation in clusters. And when I say the gas, I really mean the gas mass profile. This is the cumulative mass profile in clusters as a function of cluster radius. And this is the gas mass abundance as a function of halo mass. And what you can see here is a result of simulation work where the same initial conditions in the cosmological simulations were run with different hydrodynamical assumptions, so different assumptions on the gas physics. This black curve here is what you would get in a purely dark matter simulation. And these color curves are what you get when you turn on these various feedbacks. So the fact that the gas cools, forms stars, blows up supernovae, or form active galactic nuclei. And what you can see is that there's a dramatic effect on this cumulative mass profile of the gas. And the way you should interpret this curve is basically that this feedback from galaxy formation has pushed the gas in the outskirts of your cluster. And so measuring this mass profile of the gas is a very sensitive probe. It's a very good way of constraining the feedback inside your cluster. So that's one reason. But of course, you might not be interested at all in galaxy formation inside galaxy clusters. You might care about cosmology. And arguably, in that case, you should still care about the gas inside galaxy clusters. And one reason for that is that baryons, what cosmologists call baryons, so the ordinary matter, makes up 20% of the total matter. And so if you want to learn cosmology from, say, large-scale structure, where you need percent precision on your matter power spectrum, you might need to understand where this 20% of your matter budget is. And in fact, that's the effect of matter on the small-scale power spectrum that I showed in my second slide. So I hope everyone is completely convinced by now that you should all care about gas inside galaxy clusters. And this is where the kinematic Sunyaev-Zeldovich effect comes in. So this effect is simply the change in the energy of CMB photons as they bounce off moving galaxy clusters and get to us. So it's a very simple effect. It's just a Doppler shift, the same you would have if a photon was bouncing off a moving mirror. Because it's a Doppler effect, it goes as V over C, where V is your line of sight velocity. And it also is proportional to how good of a mirror your galaxy cluster is. And this is quantified by this optical depth to Thomson scattering, which is basically the line of sight integral of the electron density times Thomson cross-section. So why is this effect useful to probe the gas inside galaxy clusters? Well, you can see that this effect has a nice property that it's directly proportional to the electron density. So your gas is ionized inside the galaxy clusters, and so the electrons basically probe the gas. So you have a quantity that's linear in your gas number density. So you're basically counting all the free electrons. So if I could measure the KSZ effect from a halo, I would know exactly how much gas is in there. So that's the hope. Another value of this method compared to other ways of probing the gas inside galaxy clusters is that it is simple, it's very clean, it's just linear in the density. So if you know about the thermal Sunyaev-Zeldovich effect, what you're probing there is density times temperature. So getting at the density is difficult if you don't know the temperature profile. And what you get in X-ray measurements of clusters is more a combination like density squared root of temperature because it's Bremsstrahlung emission. So here you have a clean probe that just counts all the free electrons. Because of the scaling with mass, because of the fact that it's linear in density, you are sensitive to lower mass halos than other probes are. And because the Sunyaev-Zeldovich effect, relative brightness with respect to the cosmic microwave background doesn't depend on redshift, you're basically able to probe galaxy clusters at high redshift. So this sounds like the KSZ effect is great. Of course, there are drawbacks, and one of them is that it's a very small effect. So the typical signal from a galaxy cluster might be around 0.1 microkelvin, which you should be comparing to something like 100 microkelvin. So it's a very small effect. And furthermore, the KSZ effect does not distort the black body spectrum of the CMB, meaning that it takes a black body and it turns it into a black body of a different temperature because it's a Doppler effect. And because of this, you can't just separate it from the CMB with multiple frequencies. So what I'm showing here is, again, a CMB power spectrum. By now, you'll have seen it many times as a function of scale. And this blue curve here, the blue curve is the lensed CMB, so just the CMB. And the red curve is the kinematic Sunyaev-Zeldovich effect. And what you can see is that this KSZ signal dominates over the CMB temperature at very high L or very small scales. And again, from multiple frequencies, you can't just distinguish the two. The other components that you typically have in your CMB map and that are an issue are detector noise. So this is typically white noise, and I've shown it in dashed lines, and other astrophysical foregrounds. Now, these other astrophysical foregrounds have different frequency dependencies, and so the hope is that you will be able to remove them, or at least a large fraction of them, with multiple frequencies. So if you just think of your cleaned CMB map with only CMB, KSZ, and hopefully low detector noise, you would basically just detect the KSZ directly by looking at your map on small scales. So this is one way to detect the KSZ, and looking at just the temperature power spectrum. And in fact, people have upper limits that are close to detection on the size of this effect with this method. There are many more methods to detect the KSZ, and I'm not going to talk about all of them in detail, but I'll be happy to answer questions if you are interested. The methods I'm going to talk about relies on this velocity reconstruction from the density field. And so this is what I'm going to tell you about. And the reason why we use this velocity reconstruction is the following. Naively, what you would want to do is you would take your temperature map. If you know there's a cluster here, you just look at the temperature there. If your signal noise is not high enough, you average it on the position of many clusters, you do stacking. And you would hope to get a nice average profile of your cluster. The issue with KSZ is that since it's proportional to the velocity, the sign alternates, depending on whether the object is moving towards you or away from you. And so if you just average at the positions of clusters, what happens is that your signal averages out to 0. So that doesn't really work. But on the other hand, if you have a handle on the line of sight velocities, you can average your temperature maps weighted by this velocity estimate that changes sign. And now your signal no longer averages to 0. So I hope that makes sense. If not, please ask me. Let me now tell you how we get this estimate for the velocity, how this velocity reconstruction works. So far, every time I've been talking about velocity, what I really meant was peculiar velocity. So that's the motion on top of the Hubble flow. And it turns out that because of mass conservation, in the linear regime, which you can just rewrite as this, variation of the density plus divergence of velocity is 0. In linear theory, you can actually invert this equation. And this gives you an estimate of the peculiar velocity as a function of the density field. The intuitive content of this equation is very simple, and it basically just says that if you have more matter here, it's because stuff has been moving towards it. So that's basically all of what this equation says. And this is how the velocity reconstruction method works. Let me just illustrate to you how this works. And this is velocity reconstruction data from Kendrick and Marina Vargas Magana that I'm going to be showing to you. So this part was really crucial in making the project possible. But what you see here is this funny shape is just the footprint of BOSS, which is a spectroscopic galactic survey on the sky. So this is just a map on the sky. But because we have redshifts for all of these galaxies, we actually have 3D information. So we can put these galaxies in a 3D box. And once you have this, you can just make a 3D grid, estimate the density field, take this funny gradient of the density field, and get an estimate for the velocity. And this is basically what the line of sight velocity would look like, where color indicates whether the thing is moving away or towards you. So this method was implemented by Kendrick and Marina Vargas Magana. So again, we took these galaxies. We took only the ones that overlapped with our small CMB map. and I just say small in terms of area. And so we're left with this number of objects, and these galaxies are good tracers of the center of galaxy groups. So they're good tracers of halos, which we hope will have a detectable KSZ signal. And then the velocity reconstruction is performed, and so for each object, we now have an estimate, V reconstructed, for the line of sight velocity of this galaxy. So for each object, we have an estimate of the reconstructed velocity, and now we'd like to compare this to the temperature we see in the CMB map. And without going into the detail of the measurement, basically, since we're after the gas profile, what we did is we just sort of take an aperture around the object and average the temperature there, and then vary the size of this aperture. And that gives you information about the gas profile inside these halos, which is the thing we're after. Now, whether we've detected or not the signal can be formulated as this hypothesis that we're testing. Does the fluctuation in temperature that we see in the map relate to the reconstructed velocity plus noise? And to test this hypothesis, we introduced this just fitting parameter alpha. And intuitively, if you fit for alpha and find it consistent with 0 in your data, it just means you have detected nothing. If you find it consistent with 1 because of our normalization, it means that within your aperture, you've detected as many electrons as you would expect from cosmological abundance. And again, because we vary the size of the aperture in this temperature measurement, we vary the size of the aperture, we get information on the profile of these halos. So let me show you what we obtained from this data. So again, this parameter alpha, which you can sort of interpret as a cumulative electron profile because you're increasing and increasing the size of your aperture as a function of the size of your aperture. These data points are basically our measurements. What you can see is that at large apertures, the measurements become very correlated. And that's in part because a larger aperture contains the small aperture. And so most of it is correlated, and that's related to the noise in the CMB maps. So, right, these points are correlated, as you can see. And so overall, it's measurement at 3 sigma. So it's marginal significance. But what you can see is that the shape here basically probes the cumulative electron profile, which is the thing we're after. And while you might ask, what do you learn from a 3 sigma measurement? And might expect the answer to be not much. I find it encouraging to see that already with this kind of precision data, you're able to say interesting things about the gas profile. So this red curve here is what you would get if the gas followed the dark matter as parameterized by this profile, the Navarro-Frank-White profile. And what you can see is this profile really doesn't fit our data. So even with this low significance data, you can already see that basically the cumulative profile starts growing farther out than the dark matter does. And that tells you that the slope of the gas profile is more shallow, that the gas is more puffed out. This is encouraging. If it stopped there, then I suppose that wouldn't be super exciting. But what makes me very interested in this method is the fact that these error bars are going to shrink in the next few years. And I think conservatively, reasonably, I'm very confident that these error bars will basically be divided by a factor of at least 30. And let me explain what I mean by that. So this is some very simple scaling of the signal-to-noise ratio. My signal is proportional to the mass, the gas mass, so the mass of my halo. And my signal-to-noise increases as square root of objects, just because you're stacking objects. And so if you just ask for, if I compare the data that we have now with what we expect to get in the next few years, just square root of n tells you that you'll get something like a factor of 30 in signal-to-noise. So there's very few ways to get around this. So basically, your errors will decrease by at least this factor. And that's not even factoring the improvement in the CMB map, which at the end of the day, I expect to be a few. So basically, in the next few years, what I think is inevitable is that the signal-to-noise that was of order 3 will go to order 100. And at this point, you start to be saying really interesting things about the gas profile. Now, to give you just an example of what you can say about the gas profile, here's a schematic idea. So again, the kinematic Sunyaev-Zeldovich effect is proportional to this optical depth to Thomson scattering, which is proportional to the number of electrons and the line of sight velocity. So by measuring the KSE effect, like I showed you, you get a handle on the gas density. Now, if you have the CMB map, for basically the same price as measuring the KSE, you get the thermal Sunyaev-Zeldovich for free. This is the effect of CMB photons, again, bouncing off the galaxy cluster, but not the bulk motion, the thermal random motions of your electrons. And this shifts the energy of your photons on average, and scales as follows. Optical depth to Thomson scattering times thermal velocity squared, which is basically temperature. So here you have temperature, and here you have density. So you're basically probing the thermal pressure of your electrons. And if you have these two ingredients, you have basically most of what you need to write a Virol theorem. So if I write a Virol theorem for the gas inside my clusters, what I get is a relationship between the gravitational energy of the gas in the potential of the gas plus dark matter. This would be schematically the volume of my cluster. And then you get the sources of support. So thermal pressure support, anything else that supports your gas, and this has found to be important. And finally, a surface pressure term. The KSE measurement will give you the gas mass profile. And so basically, you'll be able to estimate the gravitational energy. The thermal SE measurement will give you the thermal pressure support. And so these two measurements combined will basically tell you something about the other sources of support inside galaxy clusters, things like turbulent motions that are pretty uncertain, and would help constrain galaxy formation. And because of the high signal to noise, this is something you'd be able to do as a function of radius. So basically, you'll be able to say a lot of things about the thermodynamics of your gas inside galaxy clusters beyond just density. And I think this is going to be very powerful in constraining galaxy formation profiles because you get really a handle on how much energy is injected, basically the whole thermodynamics of your gas. So to conclude, I presented to you some evidence for the kinematic Sunyaev-Zeldovich effect with temperature data from ACTPol and galaxy data from BOSS. Hopefully I convinced you that this method is a powerful baryometer in that it tells you where the ordinary matter is, where the gas is. I'm very much convinced that the signal to noise has increased a lot, and at this point, I think you can start to say a lot of very interesting things about gas thermodynamics and feedback processes inside clusters, which eventually you will need to understand if you want to use the large-scale structure on small scales, where these baryonic effects are important. So that's it. Thank you. Yes?
So at what point will there be meaningful enough information that you can really tune in body simulations and get the baryonic physics right?
Mm-hmm.
Are we going to get there in stage 4 of this unfolding increase in signal to noise, or are people looking at that?
Right. So I think it's definitely a complicated question, and it's starting to be the limiting factor for using the large-scale structure because so I talked about this number of modes and the fact that when you probe the universe in 3D, you have much more than when you just look at the surface. But extracting these modes requires going to small scales where these baryonic effects are an issue. And currently, basically the state of the art for these hydro simulations is that you either have very realistic simulations in which you have a lot of free parameters that people have set. These simulations take a lot of time to run, and so you're not really able to vary them all consistently and see what you've understood. So basically, currently, I don't think there is a hydro simulation that fits all of the astrophysical data that we have. So we don't have a fit, and when we have sort of a fit, we don't really know how degenerate the different parameters are. And so this is why people are sort of moving, in some cases, towards semi-analytic models, where your physics is less realistic, but you have a handle on which ingredient does what, and can vary them quickly. And I think these measurements will help a lot with this. then will they be the definitive constraint on this? I don't know. Yes?
I guess if you look at the thermal SZ effect and make some assumptions about temperatures, you could extract the density profile as well. So has anybody done that? And if so, how does it compare with
the KSZ profile?
Yeah.
Yeah. So I think given given a thermal SZ and a kinetic SZ measurement, there always exists a temperature profile that will make the two match. And so this is sort of why we think of it more as measuring KSZ and TSZ and considering the temperature from it.
The temperature must be, I would have thought it was calibrated more or less from some X-ray.
Right. So
cluster surveys.
yeah. So something I should have pointed out is that we're going to scales that are really hard to probe with X-ray. So to give you an idea, around here is basically the virial radius of our objects. And in X-ray, it's very difficult to probe the gas beyond this. And the reason for this is because, well, X-ray measurements typically have higher resolution than our CMB experiments, which is great for probing the center. When you go to the outskirts in X-ray, your photon counts goes down a lot. And all the energetic particle backgrounds on the detector will start to be very limiting. So going beyond this is not impossible in X-ray, but it's extremely expensive. So people typically don't do it.
Okay. Maybe E-rose in the future or something.
Right. Yeah. So you basically, I think you want an X-ray measurement in low Earth orbit, and the magnetic field of the Earth protects you from these energetic particles that are background. So that's sort of one of the selling points of KSZ. So I said the fact that you can go to high redshift, but also the fact that you can probe the outskirts of clusters. Yes?
I was wondering, so since the KSZ is a line of sight integrated quantity, do you basically have like one cluster on the line of sight, or is it the mass profile that you have to consider?
Right. So that's a very good question. So it turns out even with our sort of cluster sample, which is incomplete, when I look at one cluster, there are more that overlap on the same aperture. So then what that does is that if these clusters are far enough from mine, their velocities will be uncorrelated. And so they will add a signal that has a random sign. So what that means is that in that case, it's just a noise. So in that case, it's not an issue. But if this extra cluster or this diffuse gas is close enough to my galaxy cluster, then the velocity will be correlated. They will have the same velocity. And so they will add to my signal. And the way we think of this is basically the same as in galaxy lensing, where you have a two-halo term. So I think I probably have an illustration to show you. All right. So if you look at this this plot right here, this curve is basically the same as my measurement, but on a simplistic simulation to try to just test the estimator. And these curves that I labeled one halo and two halo basically mean one halo is really that cluster's profile, and two halo is the signal that I get from all the matter that's correlated with this profile. And basically what you get in principle is the sum of the two, these black data points. So in the scales that we're able to measure right now at small apertures, we don't see it yet, but we'll be able to see it in the future. And what that part of the curve tells you is basically where is the diffuse gas around these clusters. So you'll be able to measure the bias of these free electrons. So that's in itself another interesting measurement.
Yeah, so the trick is because of the correlation with the velocity field that then is redshift dependent. So the velocity field you have a different redshift density. And so there is no, like for the KSZ, you cannot get something like a redshift dependent KSZ measurement. That is always an integrated thing. Or could you have, like, if you had spectra, for example, if you would get spectral measurements, could you tell that?
Right. So in the CMB temperature map, everything is projected. However, if you have a cluster sample at different redshifts, you will be extracting the contribution from this redshift to the temperature map. So in a sense, you can measure the KSE at different redshifts. Does that make sense? Or so right, sorry. So so in this measurement,
the temperature that you measure is like a 2D field.
Exactly.
So integral over everything.
Over the whole, yeah.
And you do correlated.
That's right. So in a sense, with this measurement, where we have a known galaxy sample, we're extracting basically just the KSE from these halos and correlated matter around them. But if you split your sample in different redshifts, you'll be extracting the KSE signal at different redshifts.
But if I take this evidence on its face value, is it still telling me there's a missing baryon or gas problem? Or
No, so of course, right now, there are big error bars because with 3 sigma you have over 30% uncertainty. But at this level, there's no missing baryon problem. And I think most people would agree that the missing baryon problem is mostly the gas being pushed farther out. And if you're able to look farther out, you'll see these baryons. Yes?
So if you extend that question and imagine with a future experiment, like DESI or something, you could slice your map into different redshift bins, and then you could actually measure, F sigma 8 as a measurement of the growth of structure principle.
Right.
Is there any chance this would be competitive with anything else?
Yes. So this is tricky. So
you'd have to, I guess your gas profile would become a nuisance parameter or something that you'd have to marginalize over.
That's right. So if I go back to something I didn't say and probably should have. So this KSE effect is proportional to how many electrons I have times the velocities. Now, the velocities are a very interesting cosmological probe. And like you said, they probe this little f, the growth rate of structure, times sigma 8, the amplitude of fluctuations. And measuring this little f is very useful also to constrain dark energy and modifications to gravity. In this case, though, if you want to get the little f from velocities, you have to know your baryon profile very well. So basically, with the current way we know this little f, this growth rate of structure, is from redshift space distortion, is arguably one of the best ways. And currently, this is measured to like 5%. And so this is just saying BOS, redshift space distortion, gives f to 5%. Now, if you believe in general relativity and you plug in the cosmological parameters we know with their uncertainties, I think you then know this little f to better than 1%. So then it's a bit tricky to be competitive with KSE because it would mean you would have to know how many electrons are in your clusters to that accuracy, which seems pretty hard. So this is why we mostly took the point of view of using this measurement as a probe of the gas as opposed to a little f. However, there's also information in the shape of that signal. So one thing I didn't show here is that you can measure the signal as a function of separation between pairs of clusters. And when you do this, you're actually probing the correlation function of the velocity between your clusters. And this function has an amplitude, which again goes as tau times v over c, but it also has some shape. And people have worked out how well you can use the shape to constrain things like modifications to dark energy or neutrino masses. So in most cases, it's not super competitive, but if you have a modified GR that introduces a scale dependence in the growth, you might hope to see it.
But wouldn't it be true then that, again, redshift space distortions comparing different Ks
would be able to do the same thing?
might be better?
That's likely the case, yeah. Another thing, though, that you can hope to learn from KSE, and which is really unique, is properties of reionization. And so, like this was said, your KSE map is projected, so it's hard to disentangle reionization from late times from these clusters, and they have comparable signals. But there are methods to try to extract both. In fact, Kendrick and Simone Ferraro were the first to propose one of them that basically looks at higher order point functions and lets you pull out the signal from reionization and late times. So this is yet another thing you could learn with KSE. right, thank you.